evaluations are due today by 4 p.m. The last sapling weekly skills check is posted right after class. I'll also post the last PLA on sapling for Friday. For the skills check, unless you want to be doing a lot of work on the night before the first final exam on Tuesday, I would probably work on that now and get it done. We will probably finish all lecture material on Friday, so there won't be any lecture material on Monday that you would probably. So we're going to that now, and we do have one more reading that we're doing, and that is for Monday. That is posted now, and then the very last PLA will also be on Blackboard, like it was for the last couple of readings. So for that's like number 34, I think. That one, don't go to sapling; it won't be there. It's going to be on Blackboard instead, and I might post that early too, just so you have it for the weekend. Well, you have it. But I might post it today. So if you're a W student, yes, you need to write a reflection for this last reading assignment, and that is already up on Blackboard as well, so we'll do that when we can. And Christmas party is this Friday, 3 o'clock on the 3rd floor, and then I had too many announcements, so we can go to page 2. So, extra credit, that's due Monday, details are on Blackboard, and the choice is either the video or the paper on some readings. And that's up to 5 points. I think that's what I said before, right? And then another extra credit opportunity, I do this every semester. So to encourage you to complete your course evaluations, not just for my course, but for every course that you are taking, if you go and you finish them all, and then send me a screenshot of that page that says, congratulations, you completed all of your course evaluations, and really all I need is that you're done. And somewhere on that page is sometimes your login ID, so I know it's yours. I just need a picture of that, and I'll put that up on Blackboard as well, so you can just upload a JPEG, as long as it's an image file that I'll be fine. So I will put that up later today, and that will also be due then by the time you come to the final exam. If you bring me a hard copy of the final exam, that's also okay. Then the final exams, Wednesday from 1 to 3. And I had misremembered. I thought it was 50 points over Chapter 12, but it's not. It's only 30 points over Chapter 12 material. I will go ahead before the weekend post last year's version of that. The cumulative portion is multiple choice questions. So it's 50 multiple choice questions, 2 points each for those, and that's over all material for the semester. That will be on a Scantron, so please bring a pencil so that you can fill it out with pencil. And then if you're a W student, you only have to take the 30-point part of the exam. You can skip the cumulative part. Yep.
Cumulative is the Scantron of the Chapter 12?
Will be handwritten.
Okay.
Yeah, Chapter 12 is handwritten. It'll be similar format to previous exams. But it'll only be 1 page.
Doctor, do you want us to bring our own Scantron?
No, I'll bring them for you.
Partial credit on the multiple choice?
Nope, this is 2 points.
That's good.
However, there's legitimate multiple choice questions. There's only one right answer. There's no ambiguous.
Oh, thank you.
I'm like Dr. Whitworth, all of them. None of them. Yeah, but that's why he doesn't do Scantron. So let you mark all of them as correct.
Okay, you got your eye clickers ready? Here's the good news, right? You lost it, right? It's gone. This is the last eye clicker, right? So well appreciated. So I have acetylcholine esterase and catalase, and I have some constants here at Km for each and K cap, and then that ratio. And first question is, which of those two enzymes has the higher binding affinity for its substrates?
It's E? Okay, thank you. Apparently it's E. It's always E. It's always E. Isn't there research on the most, like if you have more idea about which questions usually like or something?
Oh, split.
Ooh. Or E.
So you have to be careful. First of all, which term do you look at?
Yeah.
Km. Okay. And Km is kind of an inverse thing. So you want little numbers for tight binding. So which one is the smallest number there?
A.
It is A. Yeah. So the smallest Km is the tightest binder. All right. So then, which of those two is more kinetically efficient at your rate limiting step? So you're looking at catalysis rates now.
Uh-oh. Why is one clicking right? Oh, there we go. Why is it clicking red? You heard it? It was clicking red. Did we have a workbook for physics today?
Okay, most are saying B.
Yeah.
Okay, which one are you looking at?
K-cat.
K-cat, and this is a turnover number, so the biggest number is going to be the fastest at the catalytic step. Okay, and then third one, which is the overall most catalytically efficient enzyme?
C? Okay. Thank you. Don't press C.
Alright, so most of you are saying B. Why did you pick B? My K-cat ratio to Km is bigger. Okay, but I'm going to tell you that wrong. Okay, so both of those are at a diffusion control limit. So this one is 10 to the 8th, 10
So
to the
let's
8th.
see.
And making the assumption that the units here are inverse or inverse seconds, although I put the units on there, so it makes it kind of hard to tell. But if it is inverse molar, inverse seconds for that ratio, then you are at that 10 to the 8th, 10 to the 9th range. And so at that point, it's just diffusion of molecules through solution that controls the rate and has nothing to do with how well something bonds or how fast it can turn over the substrate into product. So at that point, I probably wouldn't worry too much about the magnitudes. The difference there might just be experimental error at that point.
So it's C.
So the answer is C. Yes.
I told you.
Trick question.
All right. So we got lots of equations to do today. So analysis of kinetic data. And we're going to do an example here. Looking at the decomposition of hydrogen peroxide, which is actually catalyzed by catalase, which was the one that we were looking at in our quicker questions. And it makes a couple of waters and an oxygen molecule. And hydrogen peroxide is going to be a aqueous solution. Water is a liquid, and oxygen is a gas. And you see that all the time, hydrogen peroxide bubbles or reproduce. This is something that you can measure. You capture the gas. Okay, so remember, you've got to have something that you can monitor, either disappearance of your substrate or the appearance of a product to get the rate. And in this case, the easiest thing to monitor is that gas formation. And so when I look at my initial rate here, I'm really looking at the appearance of oxygen with time at time equals 0, or pretty close to it. volume or moles of O2 produced. If I have a really high concentration, I might see something that looks like that. So this is our high concentration of hydrogen peroxide. And maybe it's this getting towards the Vmax over here. And if I have a lower concentration, it's not going to go as fast. There's no concentration effects rates. But it's still going to be heading towards the same Vmax in the end. If I'm looking at Vmax, what plot am I looking at? What goes over here?
Can. Not whenever.
If I want to draw Vmax on that line, what is that axis?
The velocity.
It has to be velocity, right? Not moles. I'm sorry. And versus what? Substrate concentration. Yeah, I'm jumping ahead to the next plot. So sorry about that. So scratch the Vmax. This actually represents, this is going to level off because you're running out of substrate. When I look at this plot, so this is just molar volume of oxygen gas produced with time. What you should hopefully see is that towards the beginning here, I can probably pull out some data that is approximately linear. It eventually isn't anymore. It starts to curve. But right here at the very beginning, I can pull out some data that looks linear. And so this is my initial rate that I can pull out. It's going to be in moles of oxygen per time. This is going to be my rate. So you're going to do this again for multiple concentrations of hydrogen peroxide. So this first one was the kind of higher concentration, and this is a lower concentration here because it doesn't go as fast. So we're going to do this again for multiple concentrations of hydrogen peroxide. And I'm going to record initial rates for each. So we have our equation, our Michaelis-Menten equation. That looks at rate and substrate concentrations. And then we want to be able to pull out this Vmax and this Km return. We want to be able to calculate those. We can do that if we plot it, our rates and our substrate concentrations, but it works better if we do this in a linear form, so we take an inverse to get a linear equation. And after you move some things around, you're going to get 1 over V naught is equal to Km divided by Vmax times 1 over the substrate concentration plus 1 over Vmax. So that's another one that you should remember. This is a double double reciprocal. And this is used to generate line rubric plots. So if 1 over my initial velocity is y, then the Km over the Vmax is my slope. 1 over substrate concentration is x, and then V is my 1 over Vmax. Plot this. So again, this is 1 over my substrate concentration. This is 1 over my initial rate that I measured. And then I'm going to get a bunch of points. That if our enzyme follows the Kalos-Knighton kinetics, and all of our assumptions were valid assumptions, it should be linear. And then I'm going to do a best fit line. Sorry, I'm doing something like that. Where my y-intercept is 1 over Vmax. And my x-intercept is a negative 1 over Vmax. So with that best fit line, we can then calculate what our Km is and what our Vmax is. And then I reminded you this last time that you have to be careful about a few things. Remember that your substrate concentration has to be much, much bigger than your enzyme concentration. You get big errors with small differences in both your initial velocity or your substrate concentration because it's an inverse. So multiple trials help with that. And you should fix substrate concentrations above and below your expected Km. So remember that your Km is also the substrate concentration at which you reach 1/2 maximum velocity. And so if you're thinking that in terms of substrate concentrations, you want to be finding your Km when you've got points here on either side of that substrate concentration that's the same as your Km. You wouldn't want your Km to actually be down here, or your Km to actually be way up there. You want it in the middle of the line, in the middle of your data. So in your homework, you did a few of these, right? And apparently one of them has some reason like the fact that you were rounding, you had to remember your stick fix. What's that thing? They let you mess up within like 10% of what the expected value is, but if you start dropping lots of significant figures, that usually bumps you out of that 10% range. So just be careful. If they give you 3 significant figures in their initial numbers, you should probably put in 3 significant figures for it. Okay, so we're going to do examples of this on Friday and examples of this on Monday as well, where you're actually going to have to plot the data and pull out your numbers. I'm pretty confident at this point most people here can make a plot and fit some data and come up with a linear best fit line. It's not something that's so useful to do in here, so I'm going to make you do it as homework instead. So your PLA for Monday, you're going to have to prepare the data and bring in the plot, and you're actually going to turn that in for your PLA. So in the meantime, we're going to go on, we're going to talk about inhibitors. So this is a substance reduces enzyme activity. And this could be reversible or irreversible. Irreversible ones are usually toxins and poisons, and I'll talk about a few of those on Friday. Reversible inhibitors, sometimes it's an example where it is used as a way to regulate the enzyme activity, so it's not some weird thing that is not normal to the cell. Like a poison could be, but it might be something that the cell actually makes to regulate enzyme activity. There are 3 types of reversible enzyme inhibition. And the first one is competitive. So in this case, your inhibitor competes directly with substrate. To bind up the active site. And your enzyme. These usually limit the structure of the substrate. And that makes sense, right? Because they have to bind in the same place the substrate is binding. But there's something about them that prevents the enzyme from, it's competitive. It's inhibitor down the right side, and you can't bind substrate there. We go back to our equation. Plus S goes to an AS complex that then goes to the plus product. K1, K minus 1, K2 for our rate constants. This is what we used initially to set up our Michaelis-Menten equation, but now we've got something else that's competing. So we have an inhibitor that can also bind my enzyme. And this is reversible. And it's making an EI complex instead of an ES. But at this point, you don't see any reaction taking place. This equilibrium is described by a dissociation constant called Ki. And it is a dissociation constant, so this is E, concentration of E times concentration of I, divided by the concentration of I. This is a dissociation constant for inhibitor binding. That is going to affect what we look at when we're considering our total concentration of enzyme. We're going to come back to that. First, we're going to set up the equations for the types. So the second kind is uncompetitive. this case, your inhibitor binds to a site other than the active site. To prevent catalysis. Binding has to do something to the active site. Okay, so it's not binding at the active site, but binding usually distorts the active site in some way. So it's likely some kind of conformational change that happens. So back to our equation. E plus S goes to ES goes to E plus product. And I forgot to mention something here. So inhibitor binds to a site other than active site catalysis. And it, and the way it falls out of the math, what it looks like it's doing is that it binds to an enzyme substrate complex. So in other words, it's not preventing the substrate from binding the enzyme, it's just preventing the catalysis from taking place. So that means we're adding an inhibitor right here. And then we have another equilibrium. And what we're making is an ESI complex, and that's where we get no reaction. And then there's another dissociation constant for our inhibitor binding to our ES complex, and so this is Ki prime. And that is equal to our ES complex concentration times our inhibitor concentration divided by the ESI concentration, and again, this is a dissociation constant. Non-competitive, I don't know where they come up with these words, because I'm not sure, I don't even know what's correct English is. So uncompetitive, non-competitive, not competitive. One of them is very similar to the other. Non-competitive or mixed, and so if it's easier for you to remember to mixed, go ahead and call it that. Inhibition. In this case, the inhibitor binds somewhere other than the active site. To disrupt catalysis. But in this case, the inhibitor can bind either free enzyme and prevent substrate from binding, or to the ES complex. Binds either E or ES. So then when we go back to our equation, E plus S goes to ES complex goes to E plus P. I can add my inhibitor to the free enzyme, or I can add the inhibitor to my ES complex. And equilibrium here. One is dissociation constant Ki, types of inhibition that we see that actually fall out of the map when we start plotting the data. These are the sorts of changes you might observe when inhibitors present. And the competitive one is the most intuitive, I guess, to see why it happens that way. Non-competitive and non-competitive is a little harder. So now we're going to look at how does inhibitor affect Lightning-Revert flux. So back to competitive. So we said originally that E total was equal to the free enzyme plus the enzyme substrate complex, but now we also have an enzyme inhibitor complex. So this decreases the amount of active in total. So we don't have as much active enzyme as we think we do when we put that in. Competitive inhibition affects Kn, but not the inverse. And the reason for that is if you have high enough substrate concentrations, the substrate can outcompete the inhibitor. Just remember, this is all the Chatelier equilibrium. So if you have a ton of substrate around, you're going to drive the binding of enzyme to substrate forward. So substrate can outcompete the inhibitor. Vmax can still be achieved. It just takes higher substrate concentrations than normal to get there. So that this is where I was jumping ahead of my plot. So now we're doing substrate concentration versus an initial velocity. And now I can put an asymptote up here for Vmax. Initially, I might see something like this. That should cross my asymptote. This is no inhibitor. But then I'm going to see some things that won't have the same rate. So my rate has slowed down. And so this is increasing inhibitor. And that one. So we're getting more and more inhibitor. But if you take these out, eventually they're all going to reach the same Vmax at high enough substrate concentrations. Unless you can go to really high substrate concentrations, these sorts of plots are not all that useful. Because you have to get maybe really, really high substrate to get to the point where you might see this level off. And for some enzymes, you might not be able to hit the substrate concentration. It might get to a point where it's no longer soluble when it's too high. So this is where your Lightning-Revert comes in handy. So or V naught. If you look at the kilos, then it's Vmax, iron substrate concentration, and it's the Km that's affected. And the Km actually looks like it gets bigger. Where alpha, this is this modifier that we put in front of Km, is equal to 1 plus the inhibitor concentration divided by the dissociation constant for the inhibitor. So my Km appears bigger than it's supposed to be. What can I interpret about my enzyme and substrate interaction from that? Binding, weaker, right? So it looks like my enzyme doesn't bind as tightly to my substrate anymore, and that's not true. It's binding just as tightly as it always did. It's just now I have this competitive inhibitor in there. So it appears that I don't bind as tightly. So if I take my inverse, so 1 over V naught, then this is going to be equal to the alpha term times my Km over V max for my slope, times my 1 over substrate concentration plus 1 over V max. And then if I plot that, so this is 1 over my initial velocity, 1 over substrate concentration. I'm going to see something that looks like this. It's not a very good drawing. I'll just make my y-axis fatter and then I'll look. There we go. This is increasing in here. So your V max, this intercept, 1 over V max, doesn't change. That stays the same no matter how much inhibitor I have around. But my x-intercept does change because now I have this alpha modifier, and so now this is a negative 1 over alpha times Km. So Vmax stays the same, Km appears to change and it appears to get bigger. And my slope, should you care to calculate this using the slope, is alpha times Km.
I think I missed what this is all about.
Well, we do this to try to figure out how an inhibitor is working, whether it's something that is binding and competing with substrate, or whether it's an inhibitor that's binding to some other site on the enzyme. And we're saying inhibition, but like I said, your cells have very complex ways of regulating enzyme activity, and so you have negative modulators, which is just a type of allosteric regulation. And if it's allosteric, you're going to see it as uncompetitive and non-competitive, as opposed to something that is competitive against that substrate. So it's a way of figuring out how the enzyme is being regulated in the cell. Or if you're looking at poisons, trying to figure out why a particular toxin is working the way that it does, how it's affecting enzyme activity. But, these are all lines of the work plots. That means that you went in and you measured a whole bunch of rates at different substrate concentrations, where you also threw in a certain concentration of inhibitor each time. And for each set, you increased the amount of inhibitor that you were adding.
How many different concentrations?
How many would you? Well, you don't want to. Of inhibitor or substrate?
Well, just of runs, for a
You could do two, but I would not be happy with that because sometimes, like I said, there's experimental error, we get large errors because we're taking these inverses. That sometimes it's kind of hard to tell, is that really all crossing on the line? So the more trials you do, the more likely you'll be confident that it's all crossing the same point on the y-axis. So you can figure this out with only two. And you can do it, no inhibitor, and inhibitor, and you can figure it out from those two. But I wouldn't be confident with that decision without more data sets. Okay, so uncompetitive. This one affects catalysis, not binding. So in this case, Dmax is affected, but Km is not. Here's where Km is. Okay. So Vmax, your velocity, that's obvious that catalysis is slower, Vmax is slower. But binding, it's not really the binding you're looking at that point. Because remember, Km is composed of three different rate constants. You have your forward and reverse, your K1 and K minus 1, and that kind of represents the binding of substrate. But then there's K2. K2 is also part, and even though it's much smaller in magnitude compared to K1, K minus 1, it's still going to change because that is our rate limiting step. That is where catalysis is happening. So you're going to see that both of them are affected. So Km and Vmax both appear to decrease. With this type of inhibition, and then if we look at the Michaelis-Menten, it's going to be Vmax divided by, and we're going to say alpha prime to distinguish this from alpha, times the substrate concentration over Km, also divided by alpha, plus the substrate concentration. And here my alpha prime is equal to 1 plus inhibitor concentration divided by the dissociation constant, and this is the K height. And then our line Weaver Burke, 1 over V naught is equal to my Km over my V max, and notice something here, that these are both being divided by the same term. So if I take the Km term and divide it by the Vmax term, what happens to my alpha prime? It cancels. So if we write the whole thing out, the Km over alpha prime divided by Vmax divided by alpha prime, those cancel. Times 1 over substrate concentration. And with the E, we'll come out as alpha prime over Vmax. Let's just rewrite that way. So E naught equals Km divided by Vmax times 1 over substrate concentration plus alpha prime over Vmax. So the only thing that you observe change in the plot is the y-intercept. And then by default, the x-intercept, but not the slope. The slope stays exactly the same. So this is 1 over V naught. This is 1 over substrate. And you should see something that looks like this. This is increasing inhibitor. For each trial, we add more inhibitor. My y-intercept is now an alpha prime over Vmax. divided by Vmax, so your slope doesn't change. So again, this is the example where substrate binds to your enzyme just fine, just like it usually does, but then the inhibitor binds the complex and prevents catalysis. Alright, and then number 3. Non-competitive or mixed. This appears to affect both substrate binding and catalysis. So Km and Vmax change. Again, but now it's not a simple case where they both appear to decrease. So now I have my initial velocity, I have a Vmax that does appear to decrease by alpha prime. Times the substrate concentration divided by a Km that may appear to look bigger or it may appear to look smaller. It depends on which is the bigger effect, the competitive effect or the uncompetitive effect. Plus the substrate concentration. The reciprocal 1 over V naught is equal to alpha times Km divided Vmax, and remember those alpha primes cancel out when we look at that slope. Times 1 over the substrate concentration plus our alpha prime over Vmax. And if we plot that one, our initial rate and over substrate concentration, we should see something that looks like this. Increasing inhibitor concentration. My y-intercept is the alpha prime divided by Vmax, so it appears to change with each run. My x-intercept is a negative alpha prime divided by alpha Km, and it appears to change every time. And my slope is equal to an alpha Km over Vmax, and so it also appears to change every time. And so you notice that the intercept here, for the competitive, it happened right on the y-axis, and now it's going to be shifted, and it's going to be somewhere to the left of that y-axis. There is a special case if the alpha term happens to be equal in magnitude to the alpha prime term. What happened here?
They would cancel
They
each other.
cancel, yes. Then Kn does not appear to change. And only Vmax appears to decrease. So this is what irreversible inhibition looks like. they all intersect here at a -1/n. But the y-intercept is the apple prime. What piece of it do you want? Okay. Irreversible inhibition is usually some sort of covalent modification. But not always, so I have to put the usually in there. But, the irreversible, that usually implies a covalent bond being formed, and it might be a regular covalent bond, or it could be like a metal coordinated covalent bond instead. But something has been permanently altered in terms of the enzyme, so it's not reversible. So if we're studying an enzyme, maybe we know how catalysis works, maybe we don't. Inhibitors are sometimes a way to understand how enzyme catalysis works for that enzyme. So you have something that you know affects the enzyme rate. And you put it in and you look to see what type of inhibition it is. And maybe that will tell you something about how the enzyme is regulated, or it might tell you something about how the active site works. But you have to be able to describe what is happening to that inhibitor. Is it binding the active site? Is it binding to some other site other than the active site? When it does bind, does it prevent substrate from binding or not? And we have these lovely worked out mechanisms in the textbook that we went through for lysozyme and RNase A and that third one, chymotrypsin. And part of the way that they managed to determine that mechanism has involved inhibition studies. So, it's great that we already understand those, but when you're starting from scratch and you have no clue how the enzyme works, you've got to do lots of different things. So you play with pH, you play with cyclic regenesis, you try to solve a crystal structure to get an enzyme structure. You look at how inhibitors affect the enzyme. Okay, so Friday is an in-class activity. We'll talk a little bit about inhibitors at the beginning, and then it's an in-class activity.